quickly move on to the next presenter, Professor Jianchun Lee, so from UTS. So he's going to present a joint study with also with Professor Xin Zhu.
It's just one of this wonderful time and come to this meeting every year. I look forward to meet our colleagues, just catch up and also listen to their idea and what they're doing this years. And I think for the same token, and I also like to share what we're doing. And in fact, actually, I don't know, I should be thanks or maybe just because I didn't have this opportunity. And Professor Xin just supposed to present this was the last minute because some bureaucracy issue, he cannot travel to here. And he said, okay, can you do this? So I look at his presentation, realize also the same research group, a lot of details I'm not familiar with, at least have to read. So I cut half of them out and put some of the idea in there. So I can answer your question as much as I can and present things as much as I can. So, but yeah, let's see how it goes. So it's acknowledged to our student, Saeed Tali, and who is actually also working in a company now. And so the work we're going to talk about, you will see, I don't read the title now, just let's go to it. Let's skip those outline. So the idea, from my point of view, and what is structured health monitoring, particularly with AI and the machine learning, and we have challenge. A main challenge we have, and I already heard from Professor Jun Lee, and is the imbalance problem, data problem. But let's go one at a time. First is the nonlinear as non-extrapolable nature. So let me just explain what I mean by that. So if we look at this structure component or material, doesn't matter. Let's say the steel equivalent. So you have linear stage, so the linear elastic zone, and which is the operating zone, operational zone. And you also have a problem zone, which should have warning, and the yellow zone, and which become nonlinear. And then you have the hazard zone, which is you want to have that information before the failure. Okay, if you look at what most of data you get is from this zone, you'll be crazy if anyone designed the operations at this zone. But in this zone, you know the material elastic behavior has very little difference. I exaggerated a little bit, but most time probably they don't show the much difference. So we typically say, we not use stiffness. We just use the frequency. But come on, we know what's the relationship between frequency and stiffness, particularly globally. So we have a huge challenge here. And you monitor, I don't know, millions of data. They don't give you much indication about the failure. That's the issue. But we don't just flag those problems. We like to prognosis. We want to find out the current capacity, how long it goes, everything. So we actually interested in those stage. We're not interested in this stage. So that's first challenge. But then this one. Second one is okay. The machine learning and deep machine learning is very great, and then we need a lot of data to train. People probably haven't appreciated, we use a lot of them. I mean, we come to that one. We have a lot of pre-trained model. We're doing those ones, but scaling is everything. When for humans, it's very hard to interpolate large scale. So when we go to, training, what does that mean? Have a parameter training. So if you have a graph, you want to separate it, to classify it. And then what do you do? 2D, easy, just draw a line. And the dot and the cross, you draw a line. 3D, it's a bit hard. You need imagination. 4D, I don't know. But for machine, you can easily go 1,000, 100,000, easy. So in other words, actually, if we have enough data to train the system, will be able to get very good model. This is why you see even Nobel Prize recent, a lot of the interview, you look at it, they surprised with this simple transformer with tension mechanism can work so well because nobody expected. So in our community, we also start imagine, we debate, we think that should not work, but the fact is it working. Okay, and well, I mean, besides, we saw the Professor Jun Li's exploration, very pioneer, and didn't get a chance to ask question, but I don't think I should. And because it's great, you explore that area, but use large language model. If you go to Stanford, like currently, they do the large word model, which is use spatial intelligence rather than the other one. But anyway, that's the direction. It's so quickly. I mean, I check it daily. That would change. So anyway, those are issues you understand. And imbalance data means, okay, we have millions of the health data. Do we have one damage data? Maybe not, but maybe we have. Do we have one failure data? I'm sure no. See, and with this on imbalance, machine learning doesn't work. I just tell you, it doesn't work. So this is a challenge. So how to address challenge? And to answer those challenges, actually, our research group explored 3 areas. One is physics assist or informed machine learning. And particularly one we're interested on is the neural ordinary differential equation based machine learning, because we know the vibration just dominate the second order of the ordinary differential equation. That's all everything. But if you build into it, and because when you come to machine learning, 2 things are important. One is explainability and also interpretability. And the deep learning is just black box. We are not comfortable. We talk about a lot. So this is one. And the second one is transfer learning. And we're looking at fine tuning, domain adaptation, domain adaptation, joint maximum discrepancy, and adversarial discriminative domain adaptation. Those are specific ones. So we talk about a little bit. And third one is we need to utilize pre-trained neural network model. And we can see the example there. So large language model, yes, it's pre-trained neural network model. We have many of them. AlexNet, ResNet, all those. And you said, why don't I do myself? You don't have a resource. You compete with OpenAI or Tesla, and they have, billions money put into, the computation and also data. You don't. But why you need to reinvent the wheel? You don't even have a resource. So please think about this one. So, okay, give you some of the sort of idea what has been done so far. And we have 2 students working on this one. One is Xutong Zhang, and she actually done a pretty good job. Recently, she got this new the conference just came and this 910 E's. Actually, her paper has got the best paper. And that paper is specifically on the neural ordinary differential equation, and that based on the damage detection was building. And also she worked on the transfer learning-based structure damage detection, user frequency response function with this one, and also with transmissibility with different method, with the domain adaptation method on supervised. But today we actually are going to share with you on this one. On another student work, which on the bridge. And also we will touch base pre-trained the neural network as well as the transfer learning, and see how we go with that one. So we also like to acknowledge, and when we have the very powerful tool, and we can look at some problem we cannot look before. For example, a vehicle bridge interaction. So when we come to the the structure health monitoring, we could consider not just global vibration of structure, which is very hard to detecting local small damage, because it doesn't affect global change much. And so what we can do is imagine the vehicle is like a scanner, go through the bridge. The bridge vehicle interaction locally generate disturbance and signal. It's not necessarily whole vibration of bridge, but that one. And you can use that information. And it was beyond our reach before, but it's possible now. So This is the whole idea. And of course, you can utilize the inbuilt sensors, everything, and what you can do multi-modality, information fusion, whatever you can do all this. We have so many tools. We just need people boldly to explore. Because we don't know. The problem is we are lucky come to the stage, many things possible, many things are unknown. So I think it's just how brave you are to explore. Okay, we're familiar with vehicle bridge interaction, those kind of, and we can use numerical model to actually to test the U method to see whether it capture some of the feature and build after generated data. And you also can not just use simple time or frequency, use time frequency information. So you just want as rich as you can the information because somebody can handle it. So let it handle it. So when the idea is you can see, and if you cut slides through it, you'll get frequency here, and frequency here. If you cut slides over here, you have time. But this is 2D. You have many information there. And this information changes with different time and frequency sometimes different because you have moving vehicle. So it's quite exciting. And now transfer learning, I don't think I should go to detail. Basically, imagine you have numerical data. And back to more than 12 years ago, and Ulrike and I was use ANN at time, and we are doing well with ANN for numerical data that we can predict pretty good damage detection. And we do very well with experiment data. We use the experiment data to do everything also good. But when we want cross to, it doesn't work. But now we can use this transfer learning to look at use your source label data, which you have, you can generate so many. And then the experiment data, remember we said we don't have a damage case. And we have mostly linear state and not even non-linear stage. Can we do it transfer learning? Definitely is one area we can explore. I'm not saying holding solution now, I don't think so. I think we need to explore. So here's our exploration. Now, one of the easy way to do it is, okay, if we use those pre-trained the neural network like AlexNet or the ImageNet, whatever, and if you replace the last bit, they trained very well. They trained with a lot of data you don't have, and they are able to pick up a lot of feature. Those are feature, but then what you need to do is you need to replace the last layer and with your classify, if you do classification, or use your regression model. So when you're doing that one, that's a common practice. It's very easy to do it. So you use their power, use their way to classify things, but there you want what you want. You give that. It's like a interpolator, if you like. And they have power there, they have intelligence there, you just use that one. Of course, what we do is we want to explore that one, as we said, explore. So we choose 5 classifier, like a support vector machine and k-nearest neighbor, and also we didn't use this one. We use fully connected layers and also ensemble subspace discriminants and decision tree. We use this one. We set up 5 different criteria and for evaluation. Those criteria actually just looking at, have different mirrors. You can see if you use the accuracy, that's mean all the truths versus total. So the all truths. So you just let me go a little bit. Just this is truth positive, truth negative. There are truths, and or you have the false positive, false negative, and so on. And material correlation coefficient probably is a little bit overall to look at it. So each have the mirrors. So we set a parameter and we fit in, we got all the 200 samples and we trained. And then we found, and the ESD actually give you good performance. And of course, accuracy is an easy one to fit. And so with this radar diagram, you'll be able to identify which method is better. And oh, okay. That's very quick. And so I will. So then you also can use confusion matrix to look at how, how much they contribute if most people are familiar with Big Mac, Mac MAC model assurance criteria, you know the cross those correlation. But anyway, yeah, you can use also some noise to indicate things. Now I look at quickly show you the second example. Second example. So first example is fine tuning. We call fine tuning. Replace the last bit of the layer and with the classifier. But the next method, example we're going to show you is you use domain adaptation. Domain adaptation, actually, in this case, we use tree of sensor combined together and get the frequency domain, time frequency domain and graph picture because we want picture because we want to take back in pre-trained network. They are much powerful. And as for the feature extraction. So after feature extraction, we'll be able to use a regression model this time. Okay, our issue here is quite interesting. We can generate all this process level using your numerical model, but in the practical, we only have one state, one situation, which is fully pressed because you just build it, you measure it, and how those deteriorate you don't know. So this is why you can see this method is so useful because when you build in your pre-stress concrete beam, whatever the bridge, you don't have a deterioration situation. You just have one measurement, practical. That's your target. But you want to estimate what happened later. So domain adaptation and particular method is a combined maximum mean discrepancy and adversarial domain adaptation together. So you use the loss function, control your loss regression loss, MMD loss here, MMD, and also adversarial loss. And your idea is to put the two domain and together, move them together. That's how I did. This is very well because this is for the point you have 100% of the pre-stress. But if you don't have 100%, you can investigate. You also can put the uncertainty into it. So you can have all those features as a variation. You can see the variation. And then to generate a feature pattern. And then you start to put things together before you use domain adaptation. And after domain adaptation, you can data mix better. Then the prediction is hugely improved. So anyway, I think I running out of my time. I'm sorry about that one. The whole idea here is just tell you domain adaptation works. And it is possible. It's not say 100% accurate, but not just is more than better than nothing. It has some ground, you can improve it and it enable you actually predict something. Remember, if you please remember what we said before, essential issue we have. Essential issue, this is essential issue. So this essential issue can be addressed. I'm sure many of our colleagues can look into this area and we just, 2 pennies we put in and see how it goes. Okay. Thank you very much.